Hello everyone, in this video I'm going to talk about gear train. So why are we using gear train? We use gear trains when we want high velocity ratio. Let's say you want a velocity ratio of 100. You can't use a gear ratio of 1 to 100, but we can use multiple gear. Let's say the gear ratio of 5 and then 4 and then 5, so that would be 5 and 4 20 times 5 100. You will achieve that by having a gear train. So to find the overall velocity ratio, we have to know which gear is the driver, which one is the driven. But let's just look at gear 2 and gear 3 for now. This is the input, this is our output, N2 and N3. You can see this one is clockwise and this one is counterclockwise. So we already know the gear ratio, which means that if I want to find N3 to see what happens with N3 with respect to N2, I know it's inversely proportional to the number of teeth. So sorry, N2 to N3. And if I do the same thing between gear 4 and gear 3, if I want to find, okay, N4 over N3 would be N3 over N4, and so forth. If I put all of them together and replace N3 here, over there, and then find N6, the last one to the first one, we will get an equation like this based on the number of teeth. So if you pay attention, we can come up with a rule saying that if I want to find a velocity ratio, this is E, another way to show the velocity ratio, simply N6 over N2, or the velocity ratio. That would be the product of the driving tooth numbers and the product of the driven tooth numbers. So in the denominator, you have the driven tooth, and in the numerator, you have the driving. So let's see which one is the driving. So here, gear 2 is driving gear 3. So gear 2 is the driver. Gear 3 is driven by gear 2, but also is the driver for gear 4. Gear 4 is driven by gear 3, but it's not driving any gear. So gear 4 is not a driver. Gear 4 and gear 5 are on the same shaft. So this is a view on the side. So they look like on top of each other, but they're on the same shaft. So gear 5 is not driven by any gear, but is driving gear 6. So if I want to put it in this equation, gear 2 is the driver, gear 3 is the driver, and gear 5 is the driver. So gear 2 is driving gear 3, and then gear 3 is driving gear 4, and gear 5 is driving gear 6. The driven component, gear 3, I guess has a special place because it's also a driven. Gear 4 is driven, and gear 6 is driven. And then we have our equation. Each time the gears are enmeshed, the direction changes. So here, once the direction changes, here it changes again, and here it changes again. So one way to show and keep up with the direction, we can have -1 to the power of n at the beginning of our equation. So if this is our equation, and n would be the number of gears set in mesh. So here I have one set in contact, another set here, 2, and then here 3. So that would be -1 to the power of 3 would be -1, which means that the direction changes, and that's where this negative appears. But also by inspection, we can go and look at it. Okay, we have one contact, the direction changes. Here it was clockwise, that would be counterclockwise. Here it would be clockwise again, but here would be counterclockwise. One thing to note is that N3 is going to cancel from both sides, numerator and denominator, which means that the number of teeth on gear 3 has no effect. We call this gear an idler gear, which means that it has no effect in the velocity ratio. So if it has no effect, why are we using it? We use idler gear for multiple reasons. Sometimes for changing the direction. You can see that gear 3 would come into play on the number of gear setting mesh. If we didn't have gear 3, then gear 2 and gear 6 would be rotating in the same direction. If that's what you want, fine. If not, then that's good to use an idler gear. In manual transmission, in automobile, you have an idler gear to have a reverse direction. Or a spacing. If you want a space between the two gear, that's one way to space the shafts. Or sometimes gear 3 is on a shaft, and that shaft is connected to something that we need the speed and the torque of gear 3. So it could be connected to for an application if we need to get torque from this gear. But remember, for a gear train, we use this equation. In a numerator, the number of driving, denominator driven. So let's look at this example. We want to find a mechanical advantage and the velocity ratio. Let's find a velocity ratio, the product of the driving tooth number. So you have gear A is the driver, then gear C is the driver, the driven one is gear B, and also gear D. Gear B and C are on the same shaft. So the drivers NA and C, and the driven would be MB and ND. And we don't have any idler gear here. So the velocity ratio is 0.166. That's what we expected. We are going from a small gear to a large gear. That means that we are decreasing the speed and increasing torque. Again, from a small to large. So we are reducing the speed twice. So this gear train is called double reduction or two reduction. Let's write double reduction gear. What is the mechanical advantage? That would be reciprocal of our velocity ratio. So our mechanical advantage would be 6. So we are increasing the torque 6 times and reducing the speed 6 times. In most of application, that's what's happening. You are using the gear system to increase the torque. If you wanted to increase the speed, there are much better ways to do it. You can use belt system if torque is not an issue for you. But double reduction is very common. You're going to reduce it twice. So here is the driver. This is driven. This gear is the driver. And this gear is the driven. Pinion is usually the smallest one, so it doesn't mean it's a driver or a driven. So remember the terminology. So here we're gonna talk about compound gear trains. If you don't want to put your gears back to back on the same shaft, you put 2 gears, and that helps you with your gear ratio and the torque ratio. So here again, if this is the input shaft, you're going from a small gear to a larger gear, so you have 1 reduction here, means speed reduction, but our torque is increasing. And then here another reduction. So it's double reduction, and that's the compound gear train. Means multiple gears on the same shaft. And this shaft is called idler shaft. We talked about idler gear. This is an idler shaft. So they are different. Idler shaft has a purpose and changes the gear ratio, but it doesn't carry any torque. So the torque that comes in is going to get out on the other side. And these are the tangential component of the force, that if you find if we write summation of moment along this axis, these two would cancel out, and this shaft is not going to carry any torque. So idler shaft does not carry any torque. Okay, and we use compound gear train because for gear ratio, each set should not be more than 10 to 1. Again, if you want to do 30, it's better to use 6 here and then 5 here. You're not going to use a small gear in contact with very, very large gear, right? That's why we use gear train. You can reach these ratios, let's say 1 to 30, but not with spare or helical gears. We can reach that by worm gearing. Worm gives us high velocity ratio. So you go from worm, which technically has 1 tooth, to a gear with 30 teeth. So you get a ratio of 30. You're increasing the torque 30 times. So we here, as an example, we want to design a compound gearbox to provide a 30 to 1 increase in speed. So which means that here, when we are increasing the speed, we are going from a large gear M1 here to a smaller gear. Here we're increasing once and then increasing another times. Specify the appropriate teeth number. The minimum allowable number of teeth is 16. So for different gears with different sizes, you have a minimal allowable to avoid interference. But the problem has given us, there is an equation that we can find a minimal number of teeth. So here, if the velocity ratio of interest is 30, 6 and 5, then you have to achieve that. Here 6 and here 5, so n1 over n2 would be 6. We know the smallest one that we can have is 16, so we're plugging 16, which is for n2, and n3 to n4 would be 5. So here again would be 80, n3 would be 80, and that would be the number of teeth that we are going to have for all of them. N2 and N4, for the two small ones, we selected the minimum, 16. And then based on our gear ratio, we found the other two number of teeth. So we achieved 30 to 1 ratio in speed using a gear train. Another type of gear train which is more common is compound reverted gear train. So reverted, which means that if this is your input shaft, you go to an intermediate shaft or an idler shaft. This is your intermediate. And instead of putting the gear here and then go with your shaft, you bring it and put it back here. So your input shaft and output shaft, if this is the output, if this is the input, they would be in line together. So that clearly saves a lot of space, especially if you want to have multiple gears in system and multiple shafts. So that decreases the speed significantly. There's only one problem, is that these two distances has to be the same. So if you want to make them aligned, you need to make sure that you're satisfying the geometrical condition as well. So let's compare them again. Regular compound gear train and reverted compound gear train. So you can see that it takes much less space doing the same thing. But the condition that we have is that these two distance needs to be the same. That means that the radius, if I have R2 here plus R3, which is, this is R2, R3, diameter divided by 2, should be the same as R4 and R5. So that's our geometrical condition. But we know that the diametral pitch is N over D. If we assume the diametral pitch for this set of gear is the same for this set of gear, which does not have to be. These two gear 4 and 5 are in mesh, 2 and 3 are in mesh, so they don't have to be the same. But if they are the same, then if I plug in the values here instead of diameter, I can get the ratio for number of teeth. So the number of teeth for 2 and 3 should be the same as the number of teeth for 4 and 5. So let's solve a problem for a reverted compound gearbox to provide a 30 to 1 increase in speed. So here it says at least, because we will see that we can't reach exactly 30 to 1 because we have another limitation to meet. That's the geometrical limitation between the two. So we need to specify the number of teeth for each case, and the minimum again is 16. So we can go with the first one. The first one is for us is simple. We can do 6 and try to do 5 here. Let's see what we are gonna get. N1 to N2 is 6. So if we have put N2 16, the minimum, then we can find N1. But to find the other set, let's start with 5. We have the geometrical condition. N1 plus N2 should be the same as N3 plus N4. Let's plug in the value to see what we find. We know the value for N1, we know the value for N2, N3 and N4 we are trying to find it, but we have a relation. So instead of N3 I can write 5 and 4. So I can write 5 and 4 here. And see what value of M5, M4 I get. So if I simplify that, for M4 I get 18.67. So that cannot be the number of teeth. You can't have 0.67 number of teeth. So either I need to round it down or round it up. For me to get at least 30 to 1, so I want my ratio to be more than 5. So if I have to round it, I have to round this down. That's the smaller gear. That's the gear that is in the denominator. So I'm gonna round it down to 18. Once I do that, then I need to find what would be the value of N3 here. So I go back to my original equation. That was the geometrical limitation that I had. And I no longer can replace N3 to 5 and 4 because that ratio is no longer valid. You just round this down. And I'm gonna find what value I find for N3. I find 94 to satisfy. So with 94 and 18, I'm gonna satisfy this geometrical condition, which was very important. Let's see what would be our ratio. Our ratio of here N3 to N4 would be 5.22, which is more than 5, which means that if you multiply it by 6, it's gonna be more than 30. So we have reached our velocity ratio, and we have met our geometrical condition that the input shaft and the output shaft are in line. So this is the input shaft and this is the output shaft, and that's the intermediate or idler shaft. Gear train and gearbox are different. What we talked so far was gear train. Gearbox, you can get multiple outputs for the same input. Automobile transmission, you have the same input, but depending on which gears are in contact, you can get different outputs. So you're shifting gears to make sure if you want to go from if you want to have high torque, let's say gear 1, you go from small to large. Gear 5, you go from large to smaller. Gear train is that for the same input, you have the same output. There are transmission that are gear train, like Tesla transmission. Tesla Model 3 transmission is just a gear train, which means that it just increases the torque. And if you want to increase the speed, you're just the motor, the electric motor is going to rotate faster and create higher torque and higher speed if you need it. So the torque and the speed is changed at the motor, but the transmission or the train only changes that just increases the torque. It's a double reduction transmission, which means that the torque is increased twice and the speed is reduced twice. Here is a manual transmission. It's a constant mesh, which means that we are not shifting gears all the time. When we are shifting, all the gears are in contact already, and it's just we are using the hub sleeve to bring the speed of the gear to the shaft. So all these gears are rotating, and they're rotating with different speeds, and that's okay because they are loose. They're not connected to the shaft. If you want them to be connected to the shaft, use these sleeves. So here is gear 1. So this is an output shaft, so you're going from small to large, and you can see the ratio is pretty high. That means that you're increasing the torque. This is gear 2, a little bit, this one is a little bit bigger, and this one is a little bit smaller, so you have a lower ratio, gear 2, and this is a sleeve. If you want to bring the gear speed the same as shaft speed, then you use the hub, you move it to the left and to the right. And then you have it for the fourth, this is for the third gear. Again, you're going for the smaller one to a larger one, so still we are reducing the speed and increasing the torque. If you go to the fourth gear, it's almost identical, which means that you can connect input and output directly. Gear 5 is the gear that you are going from a larger one to a smaller one. So, and again, it's not much. So you're decreasing the torque a little bit and increasing the speed. So manual transmission is a reduction transmission, which means that for most gears, gear 1, 2, 3, 4, you are reducing the speed and increasing the torque. So getting the speed is easy, getting the torque is difficult. And this is an idler gear that if you want to change, go to the reverse section.